Welcome to the class on a single phase half wave control rectifier with R load. This is a circuit diagram. The input is the AC source Vs equal to Vm sin omega t. This is the SCR. This is plus and this is minus, which is representing the voltage across the SCR. This is the positive direction of the source current. This is the positive direction of the load current. This is the load resistance. To explain the circuit operation, we have taken the input voltage as a Vs equal to Vm sin omega t pi 2 pi 3 pi 4 pi. During the positive cycle, the input voltage SCR is forward bias, so we are applying the triggering voltage to the SCR. During the negative cycle, the input voltage SCR is reverse bias, so we should not apply triggering voltage. Again, positive voltage SCR is forward bias, so we have to apply the triggering voltage to SCR with a delay angle alpha. Now we start developing the output voltage waveform from alpha. 0 to alpha, no device is conducting circuit, so the output voltage becomes a 0. At alpha, SCR is on. Once the SCR is on, the current is passing from the source SCR load again return to the source. So the load voltage is equal to source voltage. So from this point you have to see how the input voltage is changing up to pi. Because of the resistive load, the current also coming to the 0 at angle pi. That current should be come from the SCR. So the SCR will be turns off at angle pi. Again pi to 2 pi, SCR is reverse bias. There is no connection between the load and the supply. Load voltage becomes a 0. After 2 pi, SCR is forward bias with the delay angle alpha. Again apply the triggering voltage to the SCR. Again the output voltage same as the input voltage up to 3 pi. At 3 pi, SCR will be turns off. This type of computation is nothing but a natural computation. If you draw the load current waveform, the load current waveform is same as the load voltage waveform, but the magnitude will be lesser because we have taken the resistance value greater than the 1. If you draw the voltage across the SCR, 0 to alpha no device is conducting circuit, so the voltage across the SCR is same as the input voltage. See how the input voltage changing, you take up the same magnitude and same waveform. Alpha to pi, SCR is on, so the voltage across the SCR becomes 0. Pi to 2 pi, SCR in reverse bias, so it is off. The voltage across the SCR becomes a input voltage up to 2 pi plus alpha. Again at 2 pi plus alpha it is conducting, the voltage across the SCR becomes a 0. After that, negative voltage. Now if you find the average output voltage 0 to 2 pi, what is the waveform is there? The same waveform is repeating. This is the repeated waveform. Now we are going to find out the area under this curve. The base length becomes a 2 pi. So 1 by 2 pi integral alpha to pi Vm sin omega t. This integration gives the area under this curve. If we complete this integration, we are getting the V0 equal to Vm by 2 pi into 1 plus cos alpha. The same circuit operation we are keeping in the table. Alpha to pi T is conducting, the output voltage is VAB. Pi to 2 pi plus alpha, no device is conducting circuit, the output voltage is 0. 2 pi plus alpha to 3 pi, again SCR is conducting, the output voltage is VAB. 3 pi to 4 pi, no device is conducting circuit, 0. If you draw the variation of the output voltage versus firing angle, take firing angle on the x-axis, output voltage on the y-axis. The range of firing angle 0 to 180. Now we have taken the three values. At 0 value we are getting the Vm by pi. At 90 degrees we are getting the Vm by 2 pi. At 180 degrees the average output voltage becomes 0. If we line join all these points, we are getting the variation of the output voltage versus the firing angle. So from this graph we can say very easily that over the range of firing angle, we can find only the average output voltage positive only. We don't get any negative value. So it gives only the first quadrant operation. Thank you very much for watching this video.